the circuit again in order to remind you that we had VG, in fact. So we had VG and then we had ZG, and then we had no transmission line, and then we had three components, in fact, and those three components were R, RL and XA, JXA, in fact, and the voltage associated over here was VR, the voltage over here was VL, the voltage over here was Vx, in fact. So yes, so here we can easily find out Px is equal to half Vx into I static, and the same way we can say this is equal to half J I XA, yes, it can be written like that, into I static, okay, so which gives us I magnitude square into XA, in fact. So Px is actually the Px has this equation, and by putting the value of, okay, so Px has this equation. By just putting value of I magnitude, we can calculate we can find out the equation of a reactive power stored in the antenna near field. So it is XA divided by 2, and the same thing, RG plus RG plus RL plus RR square plus J, and then it is XG plus XA square, in fact. So this is the equation for the energy stored in antenna near field, in fact. So what in fact we are doing is, let me summarize it. So the summary is that if you look at this circuit again, that we have in fact ZG, and then we had only ZA, okay, so and the generator has the voltage of VG. Now looking at this, where the current I is flowing through it, if you look at this, we can only achieve, because this point A and this point B actually shows the antenna terminals, in fact, from this side then antenna starts. So if you want to maximally transfer the power from the source to the load, where load in this case is actually what is my antenna, in fact. So if you want to transfer the maximum power from the source to the antenna, from the generator to the antenna, for that you need to have one condition, and that is the maximum power transfer theorem, in fact. And maximum power transfer theorem says that if Zg is actually equal to Za, then this shows the condition where the maximum power is going to get transferred. So while we were finding out the different powers, we in fact found three different powers. One was P radiated, okay, which we considered as PR, and then we found out the P dissipated, okay, and that was denoted as PL, and then we found out the equation for the energy stored, I mean the reactive power, the energy stored in the near field of the antenna, we denoted it as Px. So we found the equations for these three powers, in fact, and now we are going towards the understanding that when are we going to receive the maximum power at the output. So since we have all the power being calculated, then we can easily figure out the value of that, the equations for that power being transferred to the antenna from the generator. So if this is the condition, then which is called the maximum, let me write, maximum power transfer theorem, which we studied in our circuit theory, and it is a very famous condition that whenever the source impedance is the complex conjugate for the antenna for the load impedance, so then in that case the maximum power is going to get transferred at the output. In this case it means that if Zg is actually equal to Za conjugate, then it means that Ra, where Ra denotes the antenna resistance, which is Rr plus RL, in fact nothing else, is actually equal to Rg, where Rg is actually what is the generator resistance. Okay, now and with this condition the reactive part Xa is actually should be equal to minus Xg in order to have maximum power transfer. So in this case the current is going to get vary. I mean the circuit current in this case is going to be different now. If we consider the maximum power, if we consider maximum power transfer theorem and the maximum power transfer condition, in that case only the current is actually equal to Vg divided by Zg plus Za. And when you solve this Zg plus Za now, so this gives you the cancellation of Xa and Xg because we are adding them together, so we are left with only 2Rr plus RL. So in this case we can also go on further by finding out the power associated. So if this is the current, then in that case the power radiated by the antenna now PR. Previously we calculated the equation for this, but now we are now focusing on the the power radiated which is in the maximum power condition. So in that case PR is actually again equal to half VR and I static, and then it is equal to half again I RR into I static, so it gives us half I magnitude square and RR. And now you can easily find out the equation, because in this case the I is varied now. I is not the same as it was before, so I the magnitude has different equation. Now by putting the value of I magnitude, it gives you this equation, which is Vg magnitude square into RR divided by 8 RR plus RL square. So I would suggest you go a bit of calculation in order to find out this step, and it's easy by just putting the value. You can easily find it out. Now another thing, so the radiated power is this in this condition, in the maximum power transfer condition, and likewise the PL, which is the power dissipated in the form of heat, is now actually also equal to by the same way we calculated. So I'm not going to go in the detail. Let me write the final equation, which is Vg square into RL divided by 8 RR plus RL square. Likewise, if you notice, the power available from the generator source is the power available from the generator is actually equal to half Vg and then I static. So this gives me, when I solve it, it gives me Vg magnitude square divided by 4RR plus RL. It is going to get clear very soon, so don't get confused about it. we are going to easily cover it easily in a while. Okay. Whereas the power dissipated in generator, so let me rewrite the power available from the source, let it be P only, from the generator, that is available from the generator, that is actually Vg magnitude square divided by 4 Rr plus Rl. And now let us focus on the power that is dissipated in the generator resistance, in fact. So that is Pg. Let this Pg denotes the power dissipated in the generator resistance, in fact. So it is half I into Rg into I static, and that gives us obviously half of I magnitude square and then Rg. And if you calculate this out, it gives you